the mechanical characteristics of the products, like the stress relieving, annealing, heat treatment, shot blasting, laser printing, just mentioning a few ones. And there are also another set of activities aiming at modifying surface characteristics. A few examples are blasting, acid etching, anodization, or plasma spraying. So post-processing steps to be applied are determined by the final product specifications and also the final requirements. A few important or critical ones in the health sector are the appropriate mechanical properties and the appropriate surface properties. So in the presentation and in the entire webinar, we focus on these properties. Concerning the mechanical properties, tensile properties represents a very important group of properties, also the hardness. But there is a critical issue that has an influence on all these mechanical properties, is the porosity. In the later phase of the presentation, I will cover this issue. Concerning the surface properties, one important property is the surface roughness or the smoothness of the surface, and also the aesthetic, like in this case, for example, this sheet is color anodized. Concerning the implants, there are two very critical issues. One is the functionality of the implant itself, like osseointegration, whether this integrates easily or not. And there is another one, the cleanliness of the implant itself. So concerning the porosity, or I would start with the porosity. As-built parts always contain certain number of pores. The problem with the pores is that it initiates cracks, especially the pores which are situated at the surface of the product or of the parts. So you can see here, for example, a specimen with a crack. And also the problem with the porosities is that meaningfully decreases the high cycle fatigue performance, which is very important in case of, for example, dental frameworks, or in case of dental or maxillofacial implants. Concerning the values, the porosity values, it is considered or said that porosity between 0.2 0.5% is quite good, or considered a good printing. If the printing parameters are optimized, in that case the porosity is 0.1 or 0.2% in general, according to the scientific literature. Here you can see some images of specimens, and you can see that the porosity in this case was 0.11%, and the number of defects or number of pores was quite high, some 11,000. And as I mentioned, this can be considered a quite good number, or a quite good porosity. So since these pores creates problems for the parts, a solution has to be applied to remove these pores. One technology that is, or one process which is applied, is heat treatment. Heat treatment is a high isostatic pressure treatment carried out at high temperatures and high pressures. The temperature is in the range of 1000 degrees Celsius, while the pressure is roughly 100 200 bars. By heat treatment, the porosity can be substantially decreased, and an almost zero porosity can be achieved. Literature results are presented in this table. So, for example, here we can see that before the hip treatment, the porosity was 0.4%, and after hip, it was decreased to 0.04%. Or, well, this hip process started from already an optimized product, and in this case, before hip, the porosity was roughly 0.08%, and it was decreased to 0.012%. Certain authors even reached lower porosities like 0.01%. So we can see that the porosity that can be achieved by hip treatment is close to zero, but not doesn't reach exactly zero, at least according to the scientific literature that I have found. So the advantages of the hip treatment is that it substantially reduces the porosity, and especially at the surface. On the other hand, it has a few drawbacks or disadvantages. One is that it takes a lot of time, and not the treatment itself, but for example, the transportation of the product to the place where the treatment is done. For example, to Hungary, the nearest place or factory where this is carried out is in Belgium, which is roughly 1,000 kilometers from Budapest. Another drawback is that during the hip treatment, or as a result of the hip treatment, the product is deformed, so doesn't the shape or the geometry doesn't remain the same. And also, an additional drawback is that it, to a certain extent, increases the cost, or at least what we observed is that, well, for one part, it was not that expensive, but there was a minimum order of, if I remember well, 500 euros. So, a possible alternative to hip is the optimization of the process parameters and of the workflow of 3D printing. We also tested this direction, and here you can see some of our results. So on the left side, you can see the scanning electron microscope image of a test specimen without hip treatment, and on the right side with hip treatment. So we can see here that the porosity could be reduced practically here below 0.005%. This is the zero is which is written here is due to rounding. The number of defects was reduced to 335, which I think is a quite good result. And with hip treatment, practically all the defects could be eliminated, or at least at that resolution that was used for by the scanning electron microscope. So by these figures and results, it can be seen that similar or even lower porosity can be achieved by optimization, process optimization, and workflow optimization as by hip treatment. Well, also a very low porosity was achieved by the University of Maribor. So one of the speakers, Snehashish Pal, is from that university. So, well, the conclusion is that on one hand, applying appropriate parameters, the porosity can be substantially reduced, or even to the level of hip treatment. And the other conclusion is that when we make optimization, in that case, we have to go consider the entire process, not only the different steps or different activities, like, for example, optimization of 3D printing or optimization of post-processing, but we have to consider these activities together. And the other topic or the critical issue I mentioned was related to the surface characteristics and the surface treatment of the medical implants and implants. There is an organization called Clean Implants that investigates the cleanliness of dental implants. Their conclusions are presented here. So, but they say that what is sterile is not necessarily clean. So what they require is something that is sterile and clean. And the conclusion or the they made, or the finding that they made is that impurities on sterile pegged implants, in particular organic particles from the production or packaging processes, are highly suspected of being responsible for incomplete osseointegration of dental implant, or even loss of bone in the early healing period. So I think this really highlights and represents or suggests the importance of surface treatment, especially in case of medical implants or dental implants. So this topic will be covered by the next presentations. I mean, the surface treatment of the medical devices, and we'll address it from the topic from different angles. And the next presentation and the next speaker will be Mr. Craig Rosenblum, who is the Vice President and the General Manager of HIMED. And well, in fact, we met through 3D Hills, and the relation was generated through one of the presentations I made in 3D Hills. So the networking works, I think, quite well. Just feedback to Jenny. So I find this network very useful. And also, Craig received his degrees from the Johns Hopkins University, where at present he serves the Materials Science and Engineering Advisory Board. Craig discovered a unique application for matrix MCD, post-processing additively manufactured titanium implantable devices. And we got again in touch maybe 1 year ago, when we purchased a few blasting material from them, and we started to use that. And well, our experience is very positive. And I would like to ask Craig to present their activity.
Well, thank you very much, Zalt. I found your talk very interesting. Thank you, Jenny, also for organizing this event. Like Zalt said, we met several years ago. You know, events like this are a great opportunity for so many of us to meet and share ideas. So very grateful for the opportunity to talk today. Let me share my screen. There you go. Can everyone see this okay? Yes, okay, very good.
No, yes, it's okay. No,
now it's okay.
All
right. No such thing as a Zoom webinar without a glitch somewhere, so hopefully smooth sailing from here. Anyway, thank you again for the introduction. My name is Craig Rosenblum, and I'm here to present a particular post-processing with MCD apatitic abrasive. So this is a grid blasting process that company HIMED that I currently work in performs. Before I get into the process, just as a way of introduction, I like materials, right? I studied material science and engineering, as Zalt had said, and being able to optimize the properties of materials or enhance the surface is really what interests me in this topic. So specifically at my time at Johns Hopkins, our lab was the first lab to identify the mechanical properties of dental enamel as being quite heterogeneous. And this was a series of tests that we had performed showing intratooth, intertooth, and intraspecies variations. So some of those unique animals that are shown in the midsection of this slide, we were testing the mechanical properties of teeth and comparing them, say, in monkeys compared to human teeth and whatnot. And this was all part of a greater study, and it relates to today's topic in the sense that being able to ultimately reproduce these materials synthetically, or perhaps through 3D printing. And 3D printing, it's not done until you post-process, as Jenny made sure to include in the tagline. When it comes to post-processing and just surface treatment operations, that's really what HiMed, the company that I've been working in since 2015, is all about. So HiMed, we specialize in manufacture of different biomaterial forms, as well as surface treatments such as textures, coatings, and anodizations, and so on and so forth. So you could understand that when clients first reached out to us around 2016 or thereabouts with the emergence of additive manufacturing with components such as what's pictured here on the screen, challenges arose as far as the ability to remove partially molten beads on that 3D printed surface, various defects and imperfections, which inevitably are going to be there despite improvements to the resolution of the 3D print, surface uniformities not being present, whether it be aesthetic issues or functionality matters, visible layer lines, and then irregularities on the build plate. So, a number of different reasons are what might motivate an individual to require post-processing, but ultimately, via a process that I'm going to describe called matrix MCD, we're able to take spinal or orthopedic implants like so, and ultimately be able to perform a post-treatment operation to remove those issues. And you can see here the pre and post image that certainly the process is quite successful. Before I go into the details of the process, I want to describe MCD apatitic abrasive. So MCD is a calcium phosphate abrasive that HiMed manufactures. It's available in a wide variety of sizes, but ultimately, this is a material that's predominantly comprised of hydroxyapatite and tricalcium phosphate, and it's manufactured to be as hard as possible, right? Because this is a material that is used in a grit blasting application. And contrary to other materials like aluminum oxide and silicon carbide and other ceramics that are not compatible, these materials cannot dissolve away from the surface, and ultimately blasting with these materials will result in embedded foreign materials. Zalt concluded his slide talking about the cleanliness of the implant, and I think you'll see on this slide here that blasting with MCD apatitic abrasive, because it's a resorbable blast media, will result in a surface which is properly textured and free of any embedded grit following a passivation operation, in contrast to what is conventionally used in this field. So for those of you that are not familiar with grit blasting requires a blast media, in this case, the MCD apatitic abrasive, which is fed through a nozzle of a particular orifice at a proper flow and pressure. And based on the size and morphology of the matter, as well as the blast distance and some of these other variables, one can address the surface morphology and surface texture to achieve very fine surface roughnesses, as well as a coarser, more aggressive blast, which is conducive with a rougher surface topology. So, this is the conventional treatment that HiMed uses either to texture the surface of a machine created surface, like a CNC screw, whether it be dental or orthopedic, as well as also being able to roughen the surface prior to the application of a coating, like the coatings that I had described before, hydroxyapatite or say a titanium bioactive coating. So going back to that previous slide, the challenge that Hamed was tasked with as clients started to present us with 3D printed devices was how can we apply this conventional technology in unique matters. And the following 3 slides that I have here are a case-by-case study that show different applications and why someone might consider using MCD apatitic abrasive to enhance the surface and to perform a post-process following the 3D printed application. So the first and certainly one of the more common applications is to remove loosely adherent residual beads on the 3D printed surface. So the images that you see here are part of a study back in 2019. And this was a study that Royal National Orthopedic Hospital took on out of England. And the authors of this study alleged that this was the first study that compared the design of 3D printed acetabular cups. See, so they were not focusing on any clinical ramifications directly, but they were looking into differences in the surface. And you can see these are 3 different cups produced additively by 3 different manufacturers. And certainly the lattice is all of the lattices are quite unique, but a commonality is that residual beads, partially molten and loosely adherent, are included on this lattice regardless of the additive manufacturer that was used. And the concern, to quote the authors directly, they said that although the existence of partially molten surface beads on the 3D printed lattice is a known byproduct, the prevalence on the acetabular cups is an interesting and concerning finding because these beads might potentially be released into the body and there might be clinical implications that should be investigated there afterwards. So as clients started to approach Hamed with these challenges, we looked into applying the MCD apatitic abrasive, and ultimately for an application like so, depending on the side of the bead as well as the size of the lattice, ultimately using a granular abrasive particle size range that was properly established was the way to go in being able to dislodge beads ranging from 100 microns size and downward. And again, repeating what I had said earlier, the value for MCD is that following the blasting with this calcium phosphate abrasive, we can perform a passivation operation in accordance with ASTM F86 that allows for the surface to be clean and free of any embedded particulate in the surface. So this was the first study that I'm presenting to you today. And this remains one of the more common studies and common applications from a functional perspective. Now, of course, a lot of times clients reach out to us and they say, well, what size is necessary, right? What particle size that is? How long should I need to blast? The variables that I spoke about before, whether it be blast distance, blast time, nozzle orifice size, certainly that allows for the process to be customizable. But a study like so is a good way for us to reflect and consider the answers to some of those questions. So the image on the leftmost side is a 3D printed spinal cage that has not been post-processed. This is what it would look like following an anodizing process, following the additive print. And you can certainly see that there's quite a few imperfections on that build surface as the cage is printed. On that build plate, there's a lot of defects, as well as some irregularities within the strut size. And certainly the residual beads that I just discussed earlier are present. So via matrix MCD processing, we're able to grit blast, and with increased grit blasting conditions, we can result in a surface which is customizable that removes those defects and imperfections. So the series of images A through E, someone might think that E might be too aggressive, right? And perhaps only a moderate blast, perhaps up to C, up to D is more proper. But point being, based on the needs of the device, ultimately the process can be customized so